You gotta tell me more about this behavior that is observable, that is unrelated to the explicitly stated goal of a particular algorithm. So you looked at a simple algorithm of sorting. Can you explain what was done?
Sure. First, just the goal of the study. There are two things that people generally assume. One is that we have a pretty good intuition about what kind of systems are going to have competencies. So, from observing biologicals, we're not terribly surprised when biology does interesting things. Everybody always says, well, it's biology. Of course, it does all this cool stuff. And yeah, but do we have these machines? And the whole point of having machines and and algorithms and so on is they do exactly what you tell them to do, right? And people feel pretty strongly that that's a binary distinction, and that's what that's we can carve up the world in that way. So I wanted to do two things. I wanted to first of all explore that and hopefully break the assumption that we're good at seeing this, because I think we're not, and I think it's extremely important that we understand very soon that we need to get much better at knowing when to expect these things. And the other thing I wanted to do was to find out. Mostly people assume that you need a lot of complexity for this. So when somebody says, well, the capabilities of my mind are not properly encompassed by the rules of biochemistry. Everybody's like, yeah, that makes sense. Where you're very complex, and okay, your mind does things that you didn't see that coming from the rules of biochemistry, right? Like we know that. Um, so mostly people think that has to do with complexity, and what I would like to find out is, as part of understanding what kind of interfaces give rise to what kind of ingressions, is it really about complexity? How much complexity do you actually need? Is there some threshold after which this happens? Is it really specific materials? Is it biologicals? Is it something about evolution? Like, what is it about these kinds of things that allows this surprise, right? Allows this idea that we are more than the sum of our parts. And so and I had a strong intuition that none of those things are actually required, that this kind of magic, so to speak, seeps into pretty much everything. And so to look at that, I wanted also to have an example that had significant shock value, because the thing with biology is there's always more mechanism to be discovered, right? Like there's infinite depth of what the materials are doing, somebody will always say, well, there's a mechanism for that, I just haven't found it yet. So I wanted an example that was simple, transparent, so you could see all the stuff. There was nowhere to hide. I wanted it to be deterministic because I don't want it to be something around unpredictability or stochasticity, and I want it to be something familiar to people, minimal. And I wanted to use it as a model system for honing our abilities to take a new system and looking at it with fresh eyes. And that's because these sorting algorithms have been studied for over 60 years. We all think we know what they do and what their properties are. The algorithm itself is just a few lines of code. You can see exactly what's there. It's deterministic. And that's why, right? I wanted the most shock value out of a system like that if we were to find anything, and to use it as an example of taking something minimal and seeing what can be gotten out of it. So I'll describe two interesting things about it, and then we have lots of other work coming in the next year about even simpler systems. I mean, it's actually crazy. Um, so the very first thing is this: the standard sorting. So let's take bubble sort, right? And all these sorting algorithms, what you're starting out with is an array of jumbled up digits. Okay, so integers. It's an array of mixed up integers, and what the algorithm is designed to do is to eventually arrange them all into order. And what it does generally is compare some pieces of that array, and based on which one is larger than which, it swaps them around. And you can imagine that if you just keep doing that and you just keep comparing and swapping, then eventually you can get all the digits in the same order. So the first thing I decided to do, and this is the work of my student Taining Zhang and then Adam Goldstein on this paper. This goes back to our original discussion about putting a barrier between it and its goals. And the first thing I said, okay, how do we put a barrier in? Well, how about this? The traditional algorithm assumes that the hardware is working correctly. So if you have a 7 and then the 5, and you tell them to swap, the lines that swap the 5 and the 7, and then you go on, you never check, did it swap? Because you assume that it's reliable hardware. Okay. So what we decided to do was to break one of the digits so that it doesn't move. When you tell it to move, it doesn't move. We don't change the algorithm. That's really key. We do not put anything new in the algorithm that says, what do you do if the damn thing didn't move? Okay? Just run it exactly the same way. What happens? Turns out something very interesting happens. still works. It still sorts it. But it eventually sorts it by moving all the stuff around the broken number. Okay, that makes sense. But here's something interesting. Suppose we plot at any given moment, we plot the degree of sortedness of the string as a function of time. If you run the normal algorithm, it's it's guaranteed to get where it's going. That's the, it's gotta sort, and it will always reach the end. But when it encounters one of the broken digits, what happens is the actual sortedness goes down in order to then recoup and get better order later. What it's able to do is to go against the thing that it's trying to do, to go around in order to meet its goal later on. Now, if I showed this to a behavior scientist and I didn't tell them what system was doing is, they will say, well, we know what this is. This is delayed gratification. This is the ability of a system to go against its gradient and get what it needs to do. Now, imagine two magnets. Imagine you take two magnets and you put a piece of wood between them and they're like this. What the magnet is not going to do is to go around the barrier and get to its goal. They're not smart enough to go against their gradient. They're just going to keep doing this. Some animals are smart enough, right? They'll go around, and the sorting algorithm is smart enough to do that. But the trick is there are no steps in the algorithm for doing that. You could stare at the algorithm all day long. You would not see that this thing can do delayed gratification. It isn't there. Now, there's two ways to look at this. On the one hand, you could say, so the reductionist physics approach, you could say, did it follow all the steps in the algorithm? And say, yeah, it did. Well, then, there's nothing to see here. There's no magic. This is, it does what it does. It didn't disobey the algorithm. Right. I'm not claiming that this is a miracle. I'm not saying it disobeys the algorithm. I'm saying it's not failing to sort. I'm saying it's not doing some sort of, crazy quantum thing. I'm not saying any of that. What I'm saying is, other people might call it emergent. What it has are properties that are not complexity, not unpredictability, not perverse instantiation, as in sometimes in a life. What it has are unexpected competencies recognizable by behavioral scientists, meaning different types of cognition, primitive. Well, we wanted primitive, so there you go. It's simple. That you didn't have to code into the algorithm. That's very important. You get more than you start with, than you put in. You didn't have to do that. You get these surprising behavioral competencies, not just complexity. That's the first thing. The second thing, which is also crazy, but it requires a little bit of explanation. The second thing that we said is, okay, what if instead of in the typical sorting algorithm, you have a single controller, top down? I'm sort of godlike looking down at the numbers and I'm swapping them according to the algorithm. What if, and this goes back to actually the title of the paper talks about agential data, self-sorting algorithms. This is back to who's the pattern and who's the agent, right? He said, what if we give the numbers a little bit of agency? Here's what we're going to do. We're not going to have any kind of top-down sort. Every single number knows the algorithm, and he's just going to do whatever the algorithm says. So if I'm a 5, I'm just going to execute the algorithm, and the algorithm will try to make sure that to my right is the 6 and to my left is a 4. That's it. So every digit so it's like a distributed, it's like an ant colony. There is no central planner. Everybody just does their own algorithm. Okay, we're just going to do that. Once you've done that, and by the way, one of the values of doing that is that you can simulate biological processes, because in biology, if I have like a frog face and I scramble it with all the different organs, every tissue is going to rearrange itself so that ultimately you have, nose, eyes, head, you're going to have an order, right? So you can do that. But, okay, fine. But you can do something else cool. Once you've done that, you can do something cool that you can't do with a standard algorithm. You can make a chimeric algorithm. What I mean is, not all the cells have to follow the same algorithm. Some of them might follow bubble sort, some of them might follow selection sort. It's like in biology, what we do when we make chimeras, we make frogolotls. So frogolotls have some frog cells, they have some axolotl cells. What is that going to look like? Does anybody know what a frogolotl is going to look like? It's actually really interesting that despite all the genetics and the developmental biology, you have the genomes, you have the frog genome, you have the axolotl genome. Nobody can tell you what a frogolotl is going to look like, even though you have. This is back to your question about physics and chemistry. Like, yeah, you can know everything there is to know about how the physics and the genetics work, but the decision making, right, is like baby axolotls have legs. Tadpoles don't have legs. Is a frogolotl going to have legs, right? Can you predict that from understanding the physics of transcription and all of that? Anyway, so we made some. So you see, this is like an intersection of biology, physics, cognition. So we made chimeric algorithms. And we said, okay, half the digits randomly. We assign them randomly. So half the digits are randomly doing bubble sort, half the digits are randomly doing, I don't know, selection sort or something.
But that once you choose bubble sort, that digit is sticking with bubble
It's
sort.
sticking. We haven't done the thing where they can swap between. No, but they're sticking to it, right? You label them and they're sticking to it. The first thing we learned is that distributed sorting still works. It's amazing. You don't need a central planner when every number is doing its whole thing, still gets sorted. That's cool. The second thing we found is that when you make a chimeric algorithm where actually the algorithms are not even matching, that works too. The thing still gets sorted. That's cool. But the most amazing thing is when we looked at something that had nothing to do with sorting. And that is, we asked the following question. We defined, Adam Goldstein actually named this property, and I think it's well named. We defined the algotype of a single cell. It's not the genotype, it's not the phenotype, it's the algotype. The algotype is simply this. What algorithm are you following? Which one are you? Are you a selection sort or a bubble sort? Right? That's it. There's two algotypes. And we simply asked the following question. During that process of sorting, what are the odds that whatever algotype you are, the guys next to you are your same type? It's not the same as asking how the numbers are sorted because it's got nothing to do with the numbers. It's just whatever type you are.
It's more about clustering than sorting.
Clustering. Well, that's exactly what we call it. We call it clustering. And at first, so now think of what happens. And you can see this on that graph. It's the red. You start off, the clustering is at 50% because, as I told you, we assign the algotypes randomly. So the odds that the guy next to you is the same as you is half, 50%. Right? There's only two algotypes. In the end, it is also 50% because the thing that dominates is actually the sorting algorithm. And the sorting algorithm doesn't care what type you are. You got to get the numbers in order. So by the time you're done, you're back to random algotypes because you have to get the numbers sorted.
Mm-hmm.
But in between, you get some amount of increased, very significant, because look at the control is in the middle, the pink is in the middle. In between, you get significant amounts of clustering, meaning that certain algotypes like to hang out with their buddies for as long as they can. Now here's the one more thing, and then I'll kind of give a philosophical significance of this. So we saw this, and I said, that's nuts because the algorithm doesn't have any provisions for asking, what algotype am I? What algotype is my neighbor? If we're not the same, I'm going to move to be next to. Like, if you wanted to implement this, you would have to write a whole bunch of extra steps. There would have to be a whole bunch of observations that you would have to take of your neighbor to see how he's acting. Then you would infer what algotype he is. Then you would go stand next to the one that seems to have the same algotype as you. You would have to take a bunch of measurements to say, wait, is that guy doing bubble sort or is he doing selection sort? Right? Like, if you wanted to implement this, it's a whole bunch of algorithmic steps. None of that exists in our algorithm. You don't have any way of knowing what algotype you are or what anybody else is. Okay, we didn't have to pay for that at all. So notice a couple of interesting things. The first interesting thing is that this was not at all obvious from the algorithm itself. The algorithm doesn't say anything about algotypes. Second thing is, we paid computationally for all the steps needed to have the numbers sorted, right? Because we know, you pay for a certain computation cost. The clustering was free. We didn't pay for that at all. There were no extra steps. So this gets back to your other question of how do we know there's a Platonic space? And this is kind of like one of the craziest things that we're doing. I actually suspect we can get free compute out of it. I suspect that one of the things that we can do here is use these ingressions in a useful way that don't require you to pay cost, to pay physical cost, right? Like we know every bit has an energy cost that you have to get. The clustering was free. Nothing extra was done.
Yeah, just this plot for people who are just listening. On the x-axis is the percentage of completion of the sorting process, and the y-axis is the sortedness of the list of numbers, and then also in the red line is basically the degree to which they're clustered. And you're saying that there's this unexpected competence of clustering. And I should comment that I'm sure there's a theoretical computer scientist listening to this saying, I can model exactly what is happening here and prove that the clustering increases and decreases. So taking the specific instantiation of the thing you've experimented with and prove certain properties of this. But the point is that there's a more general pattern here of probably other that you haven't discovered unexpected competencies that emerge from this, that you could get free computation out of this thing.
So this goes back to the very first thing you said about physicists thinking that physics is enough. You're 100% correct that somebody could look at this and say, well, I see exactly why this is happening. We can track through the algorithm. Yeah, you can. There's no miracle going on here, right? The hardware isn't doing some crazy thing that it wasn't supposed to do. The point is that despite following the algorithm to do one thing, it is also at the same time doing other things that are neither prescribed nor forbidden by the algorithm. It's the space between the chance and necessity, which is how a lot of people see these things. It's that free space. We don't really have a good vocabulary for it, where the interesting things happen, and to whatever extent it's doing other things that are useful. That stuff is computationally without extra cost. Now, there's one other cool thing about this. And this is the beginning of a lot of thinking that I've done about when this relates to AI and stuff like that. Intrinsic motivations. The sorting of the digits is what we forced it to do. The clustering is an intrinsic motivation. We didn't ask for it. We didn't expect it to happen. We didn't explicitly forbid it, but we didn't know. This is a great definition of the intrinsic motivation of a system. So when people say, "Oh, that's a machine. It only does what you programmed it to do," I as a human have intrinsic motivation. I'm creative and I have intrinsic motivation. Machines don't do that. Even this minimal thing has a minimal kind of intrinsic motivation, which is something that is not forbidden by the algorithm, but isn't prescribed by the algorithm either. And I think that's an important third thing besides chance and necessity. Something else that's fun about this is when you think about intrinsic motivations. Think about a child. If you make him sit in math class all day, you're never going to know what the other intrinsic motivations are that he might be doing, right? Who knows what else he might be interested in. So I wanted to ask this question. I wanted to say, if we let off the pressure on the sorting, what would happen? Now, that's hard because if you mess with the algorithm, now it's no longer the same algorithm. So you don't want to do that. So we did something that I think was kind of clever. We allowed repeat digits. So if you allow repeat digits in your array, you can still have all the fives can still be after all the fours and after all the sixes, but you can keep them as clustered as you want. So this thing at the end where they have to get declustered in order for the sorting to happen, we thought maybe we could let off the pressure a little bit. If you do that, all you do is allow some extra repeat digits, the clustering gets bigger. It will cluster as much as you let it. The clustering is what it wants to do. The sorting is what we're forcing it to do. And my only point is, if the bubble sort, which has been gone over how many times, has these kinds of things that we didn't see coming, what about the AIs, the language model, everything else? Not because they talk, not because they say that they're have an inner perspective or any of that, but just from the fact that this thing is even the most minimal system surprises with what happens. And I frankly, when I see this, tell me if this doesn't sound like all of our existential story. For the brief time that we're here, the universe is going to grind us into dust eventually. But until then, we get to do some cool stuff that is intrinsically motivating to us, that is neither forbidden by the laws of physics nor determined by the laws of physics, but eventually it kind of comes to an end. So I think that aspect of it, right, that there are spaces, even in algorithms, there are spaces in which you can do other new things, not just random stuff, not just complex stuff, but things that are easily recognizable to a behavior scientist. You see, that's the point here. And I think that kind of intrinsic motivation is what's telling us that this idea that we can carve up the world, we can say, okay, look, biology is complex. Cognition, who knows what's responsible for that, but at least we can take a chunk of the world aside and we can cut it off and we can say, these are the dumb machines. These are just these algorithms, whereas we know the rules of biochemistry don't explain everything we want to know about how psychology is going to go, but at least the rules of algorithms tell us exactly what the machines are going to do, right? We have some hope that we've carved off a little part of the world and everything is nice and simple and it is exactly what we said it was going to be. I think that failed. I think it was a good try. I think we have good theories of interfaces, but even the simplest algorithms have these kinds of things going on. And so that's why I think something like this is significant.
Do you think that there is going to be, in all kinds of systems of varying complexity, things that the system wants to do and things that it's forced to do? So are there these unexpected competencies to be discovered in basically all algorithms? And all systems.
That's my suspicion. And I think that it is extremely important for us to, as humans, to have a research program to learn to recognize them, predict and recognize. We make things, never mind something as simple as this. We make, social structures, financial structures, Internet of Things, robotics, AI. So we make all this stuff. And we think that the thing we make it do is the main show. And I think it is very important for us to learn to recognize the kind of stuff that sneaks into the spaces.
What? It's a very counterintuitive notion.
Yeah.
By the way, I like the word emergent. I hear your criticism, and it's a really strong one. That emergent is like you toss your hands up, but I don't know the process. But it's just a beautiful word because it is, I guess, it's a synonym for surprising. And I mean, this is very surprising, but just because it's surprising doesn't mean there's not a mechanism that explains it.
Mechanism and explanation are both not all they're cracked up to be, in the sense that, anything you and I do, we could come up with the most beautiful theory. We paint a painting. Anything we do, somebody could say, "Well, I was watching the biochemistry and the Schrodinger equation playing out, and it totally described everything that was happening. You didn't break even a single law of biochemistry. Nothing to see here. Nothing to see." Right? Like, okay, consistent with the low level rules. You can do the same thing here. You can look at the machine code and say, yeah, this thing is just executing machine code. You can go further and say, oh, it's quantum foam. It's just doing the thing that quantum foam does.
That you're saying that's what physicists miss.
And I'm not saying they're unaware of that. I mean, they're generally a pretty sophisticated bunch. I just think they've picked a level, and they're going to discover what is to be seen at that level, which is a lot. And my point is, the stuff that the behavior scientists are interested in shows up at a much lower level than you think.
How often do you think there's a misalignment of this kind between the thing that a system is forced to do and what it wants to do? I mean, it's particularly, I'm thinking about various levels of complexity of AI systems.
Yeah. So right now we've looked at like 5 other systems. That's a small n, okay? But just looking at that, I would find it very surprising if Bubble Sort was able to do this, and then there was some sort of valley of death where nothing showed up, and then living things. Like, I can't imagine that. I'm going to say that if something, and we actually have a system that's even simpler than this, which is 1D cellular automata that's doing some weird stuff. If these things are to be found in this kind of simple system, I mean, they just have to be showing up in these other more complex AIs and things like that. The only thing what we don't know, but we're going to find out, is to what extent there is interaction between these. So I call these things side quests. It's like they're like in a game. Where there's the main thing you're supposed to do, and then as long as you still do it, the thing about this is you have to sort. Yeah, you have to sort. There's no miracle. You're going to sort, but as long as you can do other stuff while you're sorting, it's not forbidden. And what we don't know is to what extent are the two things linked. So if you do have a system that's very good at language, are the others, the side quests that it's capable of, do they have anything to do with language whatsoever? We don't know the answer to that. The answer might be no, in which case all of the stuff that we've been saying about language models, because of what they're saying, all of that could be a total red herring and not really important, and the really exciting stuff is what we never looked for. Or in complex systems, maybe those things become linked. In biology, they're linked. In biology, evolution makes sure that the things you're capable of have a lot to do with what you've actually been selected for. In these things, I don't know. And so we might find out that they actually do give the language some sort of leg up, or we might find that the language is just, that's not the interesting part.
Also, it is an interesting question of this intrinsic motivation of clustering. Is this a property of the particular sorting algorithms? Is this a property of all sorting algorithms?
Yeah.
Is this a property of all algorithms operating on lists on numbers? How big is this? So, for example, with LLMs, is it a property of any algorithm that's trying to model language, or is it very specific to transformers, and that's all to be discovered?
We're doing all that. We're testing the stuff in other algorithms. We're developing suites of code to look for other properties. We, to some extent, it's very hard because we don't know what to look for, but we do have a behaviorist handbook which tells you what all kinds of things to look for, the delayed gratification, problem solving. Like we have all that. I'll tell you an N of one of an interesting biological intrinsic motivation because people so in like the alignment community and stuff, there's a lot of discussion about like what are the intrinsic motivations going to be of AIs? What are their goals going to be? Right? What are they going to want to do? Just as an N of one observation, Anthrobots, the very first thing we checked for. So this is not experiment number 972 out of 1,000 things. This is the very first thing we checked for. We put them on a plate of neurons with a big wound through them, a big scratch. First thing they did was heal the wound. Okay, so it's an N of one, but I like the fact that the first intrinsic motivation that we noticed out of that system was benevolent and healing. Like, I thought that was pretty cool. And we don't know, maybe the next 20 things we find are going to be some sort of, damaging effects. I can't tell you that. But the first thing that we saw was kind of a positive one. And I don't know, that makes me feel better.